audience. So let me give you a brief outline of this presentation. First, I'll start with the introduction, objective, and the challenges. In the second part, I'll talk about the data we collected from different sources and the new forecasting models we presented. And in the final part, we'll talk about the experimental results, conclusions, and future work. So before diving in deeper within the topic at hand, let me talk a little bit about the healthcare system in the United States. As most of you know that despite spending more per capita than any other developed nation, the United States is ranked behind in key health performance indicators. And one effective solution to alleviate this situation is mobile health clinics. Currently, there are more than 2,000 mobile health clinic programs that are working across the United States. And these mobile health clinics are providing a return on investment of 12 to 1. They also reduce emergency visits. In fact, each mobile clinic results in 600 fewer emergency department visits every year. So because of all this good work, there's a need to expand the coverage of these mobile health resources. And for that, we need better resource allocation, for which we need demand prediction. The objective of our research is to present novel approaches to predict the vaccination demand in target communities, which are basically school zones and census tracts, by integrating the data from school zones and census tracts. The accurate demand prediction for census tracts is a challenging task for a couple of reasons. Number one, there is no single data source that can be used for this purpose, and we need to integrate the data from multiple sources. Secondly, the data we have is available on different spatial scales. For example, the data on the census tract level and the school zone levels is on the different scale and is often referred as spatially misaligned data. And lastly, the existing approaches rely on the perfect knowledge of the data associations, such as the geographic interactions and the covariate functions. And in this problem, we don't have that information. Now let's move to the collected data. So we collected the data for the census tract level using the American Community Survey data, which is available through the United States Bureau of Census website. In this work, we analyzed the ACS data over multiple years. In fact, we used the 5-year data for ACS, which included socioeconomic statuses, demographic features, housing characteristics, and health information at the census tract level. So these socioeconomic statuses, for example, include the income levels, the food stamps, the range of the population in a particular income bracket. The demographic features, for example, included the information on what percentage or what is the actual number of the people who are belonging to a particular race, such as African American, Hispanic, white, and others. And the housing characteristics included information such as what is the size of the household, is the house being rented, how long the owner has occupied the house for, and the health information included information such as health insurance statuses, what are the different age groups in these health insurance statuses, and so on. So based on the literature review, we selected 43 features which have strong associations with the immunization delinquency, and we presented these features with the feature matrix FC. Nextly, we collected the school zone data. So for our research, we collected data from the Houston Independent School District. And for that, we had two kinds of reports. One is the Houston Independent School District Immunization Status Report, which actually summarizes the information on the vaccination delinquency of the students. So at the beginning of each grade level, pre-kindergarten, kindergarten, and the 7th grade, the school checks which students are missing some vaccinations, and they regard these students as the delinquent students. So our focus is getting vaccination services to these delinquent students. So for the school zones, we do have the delinquency information, but we do not have the rich information on different features. In fact, for the school enrolled population, we only have the racial demographics, their economic background, as defined by the state if they are below the poverty line or above the poverty line, and secondly, the zone enrollment. And what zone enrollment means is that for a particular school district, the census tract zone to that school, only students from that census tract can be attending those school district. And lastly, the in-school clinics. So for example, for different middle schools, they have some special clinics on spot, and different schools kid can come to that clinic and get different vaccinations. And lastly, we have the partnering health centers. Mm. Yeah, we have the partnering health centers, which provide vaccination among different services to these school kids. Next, we did a small analysis on what is the variation in the demand for these vaccinations. So for example, if we look at the elementary school for these 8 different kind of vaccinations, we see there is a great variation in the demand. Similar variation is also seen at the middle school zone level. And we see that for these 8 different type of vaccinations, the demand in the year 2016, 17, and 18 is very variant. So this adds another challenge to the accurate demand prediction. That is, we cannot use a 1-year data to predict the demand for the other year. Now, as discussed earlier, only limited amount of information at the aggregate level is exposed in the school zones where the delinquency is observed. And while the rich demographic and economic information is available for the census tracts, no observations of delinquency has been made at the census tract level. Now, this presents a challenge in development of a forecasting model to predict the delinquency in the school zones and census tracts. So first, we develop an integration method based on the geographic interaction of census tracts and school zones. For this purpose, we use the school district boundaries released by the United States Census Bureau. Using the ArcGIS software and some mathematical formula as shown on the screen, we estimate the geographical interaction matrix G, whose each element Gij is defined as percentage area of a census tract zoomed to a school zone J. So what we assume is that if a census tract is zoomed to a particular school, the students from that census tract actually attend that same school zone. But note that when the population is, every census tract is uniformly distributed, then the values of the demographic function at the school zone level estimated by this geographic interaction matrix will match precisely with the values of these features observed in the school zone. But unfortunately, the population in census tract is usually non-uniformly distributed. This implies that there may exist a large gap between the values of the demographic functions observed in the school zones and what is estimated from the geographic interaction matrix. In fact, if you look at this table, what we did was we estimated different racial demographic groups for different school zones. So for example, for this particular table, we have the elementary school zone information, and we already know here that the school zone has these many different kind of racial demographic students. Then we estimated these values by estimating them from the interaction matrix in this zone census tract. We see that there is a kind of a mismatch between these two information, and that is because the information at the census tract level is not uniformly distributed. So therefore, there is a need for a new method that can actually integrate these two data sets, and then we can use that data to predict the vaccination demand in census tracts and school zones. So what we proposed was we introduced a new hierarchical forecasting model, which first finds an association matrix to align the common features between school zones and census tracts while solving this convex optimization problems. So what we have here is that we want to map the census tracts and school zone common features, which are TC and TS, TC for the census tract and TS for the school zone. We have this interaction matrix X, which can actually map these two very precisely, where Y is the any kind of mismatch that is going to, it's our surplus variable. Then we have these two kind of features, constraints actually, which actually maintains the structure of this G matrix. So while we are imposing this alignment of the constraints, we do not want these estimated and the actual matrix to vary too much in their structure. So if we skip the mathematical details, in summary, this mathematical model tries to find an association matrix that maintains the structure of G while mapping the common features of school zones and census tracts. I'll discuss further that how these features are selected. Out of all these 5 racial demographic features, we only select 3 features, And while we move to the numerical experimentation, I'll explain how these features are selected. So once we have the accurate association matrix that we identified using the previous method, we move to the forecasting model. Now this forecasting model is based on convex optimization, and it has three parts. The first part is the regression part, which is a simple regression model in which we are trying to estimate the delinquency in census tract based on the census tract features. And the second part, what we are trying to do is, since different census tracts have different features, and based on these features, we can see if two census tracts are similar or not. And based on the literature, we have seen that the census tracts with similar features tend to have similar delinquency. So this second part is basically the similarity criteria, which we have simplified through some mathematical manipulations, which represent that if two census tracts are going to have similar kind of features, they should have similar kind of census tract delinquency. And the last part actually represents the demand mapping. So using the interaction matrix XC, we want to map the demand of school delinquency to the census tract delinquency. The constraint simply is the domain constraint, which shows that the delinquency in any census tract has to be greater than 0. We cannot have a negative value. We have two hyperparameters in this equation. One is the alpha and one is the lambda. So what we're trying to do is to manage the trade-off among different targets by using these hyperparameters. When I'll move to the results, I'll show what are some of the drawbacks of this forecasting model. We also have a forecasting model which is based on non-convex optimization. So as you see on the screen, this model is actually the combination of the two parts of the hierarchical model. So instead of estimating the association matrix X separately, we estimate it while we are solving the model for the forecasting of DC and estimation of this Z. The constraints of the estimation matrix are now moved to this model. But since both X and DC are variable arguments, the objective function in the problem is non-convex. Therefore, finding the global optimal solution to this problem is challenging. And one way to address such an issue is to develop an alternative convex search method, which updates X in DC and Z alternatively by solving some convex quadratic optimization problem. So specifically for fixed X, we solve the convex quadratic optimization problem to update DC and Z. The detailed algorithm we have discussed in our paper. Now, before starting the numerical experiments, there is some pre-processing required. Essentially, we know that for different grade levels, such as kindergarten, pre-kindergarten, and 7th grade, there are different vaccinations. But to reduce the variance in the demand data, we can group different vaccinations based on their correlation in their demands. So for example, if we look at the pre-kindergarten level, we see that among these 8 different kind of vaccinations, we see that DTP doesn't show as strong correlation to the vaccination demand as other vaccinations. So we see a block-like structure in which hepatitis A, hepatitis B, HIV, MMR, PCV, polio, and varicella show a great correlation up to 99% in their demand. So we create two groups. One group contains the DTP vaccination and the other contains the demand of the remaining vaccinations. Another important question here is that we pointed out earlier is that how do we select which of the 5 common features we should select when we are mapping the demand of the census tract and school zones. So based on the recent study that we did with our collaborating partners in the UT El Paso, we find out that the racial demographics of African American population and the economically disadvantaged are the 2 strong features that are most closely related to the vaccination demand. So those 2 we select when we are mapping the common features between census tract and school zones while estimating our association matrix X. Secondly, we defined there are 43 different features that we selected based on literature review that are closely related to the vaccination demand. So we further refine these features by removing some of the features that have high correlation with each other. Nextly, in order to identify the hyperparameters in our forecasting model, what we do is that we predict the demand in all school zones but one, and then use the RMSE criteria to see what are the parameters that giving the best value. So what we essentially do is we do the leave and out cross validation for those models and then see that which hyperparameters are performing the best. And once we select the hyperparameter and the model, among the two proposed model, the forecasting model based on the convex optimization, the forecasting model based on the non-convex optimization, we impute features for the school zone. So we already have these features for the census tracts, and by multiplying it with the interaction matrix, we can create an artificial feature matrix for the school zones. Then we evaluate the model using the cross validation technique, and then for the artificially created features for the school zone, we can perform a comparison with other regression models. So we selected few regression models that are commonly used in literature, essentially the linear regression model with the principal component analysis, sparse linear regression tree, the random forest model, the neural network model, and the multivariate adaptive regression splines model. So if we look at the numerical results, we see that the hierarchical forecasting model doesn't give very good results. The reason is that since the interaction matrix is found in a different stage, it is unable to accurately map the demand between the census tract and school zone. And we see that when we integrate these two stages of the hierarchical model together and form the non-convex optimization model, we see that for each of the demand group, so group A here essentially is DTP, group B here is the remaining vaccinations, group C here is the average of all these vaccinations. We see that the RMSE values are very low, and we find a very optimal alpha and lambda and rho values. So based on this non-convex optimization model and these hyperparameter values, we estimated this association matrix X as well. And using that association matrix X, we estimated the artificial features in the school zones as well. So we created 6 different feature sets here. One are the original features of the school zones, which include the racial demographic information and the economic disadvantage information. So this information, as we referred to earlier, is not very rich in terms of features. Also, we have the original features with the in-school clinic information, which are same as the original feature, but also has a feature of in-school clinics. Next, we have the artificial features based on the hierarchical forecasting model, the artificial features based on the non-convex optimization model, and similarly, 2 sets of these as well, those of containing the in-school clinic information and those without in-school clinical information. So for each of these data sets, we select which of the feature set is the best feature set and which of the model is the best feature model. So we see that in all of the cases, the non-convex forecasting model outperforms the traditionally available models. So one additional advantage of imputing the features for school zone is that we can also estimate or also find out which features are of greater relative importance in predicting the school zone vaccination delinquency. And we find out that the population in a census tract with less than high school graduation, household receiving food stamps, enrollment in pre-K to grade 4 in public schools, the renter occupied houses, the total household income between the income group of 25,000 to 34,000 are some of the important features that are related to the vaccination delinquency. These features are inconsistent with what we have seen in the literature as well. So we see that the results are very accurate. So in conclusion, what we did was we formulated 2 kinds of models. One was the hierarchical forecasting model based on non-convex optimization, based on the convex optimization. The second one was a single layer forecasting model based on non-convex optimization model. Is anyone hearing me correctly?
Yeah, we're good.
Okay, we're good. Okay. So our new forecasting approach can predict the vaccination delinquency at both the school and the census tract level. Secondly, the vaccination delinquency can be predicted with a reasonable degree of accuracy. So for the future research, what we want to do is we want to design new effective algorithm for the non-convex optimization model. because since our data set right now is the HAST independent school district, the data set is not very large. So we were able to solve it using our alternative search algorithm. But for a large school district such as New York or Chicago, we're going to need a more effective algorithm that can minimize the time for solving this model. And secondly, we'd like to test the performance of this new model by getting large public school data sets in the country such as New York and Chicago. So that will be all from my side, and I'll leave last few minutes for questioning. Okay, let me see.
Okay, any questions for Bilal? Excellent presentation. Thank you so much.
Thank you. Okay, yeah. So if you have any questions regarding like the general idea of what we are trying to do here, or if you wanna see if you are in the similar area, then you can obviously ask many technical questions. But if you are not working in the similar area, then you may have some general questions if you would like to ask.
So what was the genesis of this project, just in general? What, how did this thing come about?
So basically, we're working with the Texas Children's Hospital, and they have a mobile health clinic program in which they provide vaccinations to the school kids.
Yeah.
And we started this program with them, and they said that they want an accurate forecasting of how many kids would need a vaccination at a particular location.
Okay.
Because currently what they were doing is they would just reach out to the school, schedule with the nurses, and then go to that school and provide vaccinations. But the problem was that when they go to that school, maybe not many students need vaccinations. So they wanted to identify what are the hot spots for different areas where these vaccinations are required. Secondly, they wanted to expand their capacities. So for example, the only hub for TCH mobile health clinic program is in the downtown Houston. So they were considering if they want to open a new location, what will be the ideal location for that particular site. So using this method, if we could predict that we did the demand for vaccination in different census tracts, then we can aggregate those census tracts and predict demand for a particular area. And then we can suggest that this is a more disenfranchised location and they should open a location of their mobile health clinic program over here. So the main idea was to help the current mobile health clinics by giving them more accurate demand prediction.
Gotcha. Did they come to you? I mean, did they know that you all did this kind of work, and did they come to you, or?
So the research was initially initiated by our collaborating partner who was at UT Health, Dr. Robert Delgado, who has moved to UT El Paso now. So it was a collaboration between UT Health, University of Houston, Texas Children's Hospital, and the research was funded by NSF.
Got it. Other questions?
I guess if we don't have questions, we can do some introduction of the listeners, which university they are from or something like that, or what they are researching on briefly.
Yeah, sure. I mean, if we want to have a little bit of a conversation, we got another 5 minutes or so. If you don't mind, if you want to just say something about yourself. Ganeshvar is ready to say something about himself, I can tell.
Hi, I'm Ganeshwar. I am a PhD student under Dr. Cash Barker at University of Oklahoma. I am currently working on prediction of restoration time of a network that has been under interdiction. So the base of the model was by Nafise, who was the speaker last week. So I'm working on an extension of her work.
Nice.
Yeah, that's all.
Mm-hmm.
Yeah, I missed last week's presentation, so hopefully I can join the rest of the presentation.
Yeah, even I missed it.
Mm-hmm.
Yeah.
I guess we've got some shy folks, Bilal. I don't know. I don't know what to say.
Yeah.
I don't know who can be more shy than me.
All right, then. We have a question.
Yeah, so for tuning the hyperparameters, we're using the root mean square error criteria.
All right, everyone. Well, thanks so much for coming by this week. We'll be back next week. Let me see we'll have Elnaz Kabir from the University of Michigan talking about some weather-induced power outage management techniques. And until then, everyone be safe, and we'll see you next week. Thanks so much.
Okay, everyone, have a great day and stay safe. Bye.
Thanks a lot, Bilal.